Right. Okay. Mm. Okay, good to go. Okay. All right. So thank you, Andrew. So hello and welcome, everyone. So today is going to also be the soft launch of a new center at the University of Calgary in that area of geothermal. So what I'm going to do is I'm going to first introduce this whole new concept of which computer? There it is, of GEOS. So GEOS is the Energy Simulation Center for Geothermal Systems Research. And the idea of it is a holistic research center for geothermal in Western Canada. So if you think of a geothermal system, what is it? It's everything from the subsurface all the way up to the surface facilities and then interacting with that community where it is built. Because if you think about it, energy systems today, which communities do they impact? Typically, the negative impacts are on the community where it's built. So let's just say the oil and gas wells, and then the export pipelines, et cetera. And then that community then buys back that energy in the form of fuels or electricity. For geothermal, there's an interesting opportunity to actually be able to directly impact that community and say, provide the heat locally through facilities that are on site and provide that power locally as well. So there's an interesting opportunity here of combining that engineering know-how with now work with the community to actually implement and develop these systems. And also if the community is on board, it's a lot easier to actually build something than, let's say, going out and saying, this shall be built here, and then having the not my backyard people show up and say, we want to put it over there, or the new ones are not on planet Earth, so we need to put them all on Mars, and then somehow ship the electricity back here. So GEOS, what we're going to be doing is we're going to be looking at end-to-end. So exploration for geothermal, the understanding of the reservoir itself, so those thermal and fluid flows, the well designs, so that's my focus, which I'll talk about a little bit in a second, the thermodynamics, those energy conversions, so what happens with that heat when it comes back to the surface, and then that whole sustainability and social license aspect in order to try and get these things built. So the funding that's been generously provided by Energy. So thank you for working with me and the university of getting this through. I know the university bureaucracy is always a fun thing to get through. We'll be focusing on 3 aspects here. So the thermal and fluid flows, the drilling and well designs, and then the surface thermodynamics and energy systems. So what I'm going to do, so just first, if we think of this at a high level, the geophysics and the geology is, where's the heat? So how do we map it and how do we work through it? So there's collaborators in geology and geophysics that have been looking through this. And there's some interesting concepts out there of how do you use geophysical data? So just say seismic data near near faults or deeper than what you typically use geophysics for to try and understand how heat flows upward. So there's some interesting work right now happening at U of C in the Denali Fault about understanding and mapping the heat flow in the Denali Fault near Alaska and how that flows up into the Yukon. Once you understand the reservoir, what types of well designs do you build and how do you actually drill them? Because again, if you think about it, on a whiteboard, you can design the most exciting well possible. Take a potato masher, it's a heat exchanger. Could we drill one of those? Well, you can get the first corner in, the second corner gets harder, and the third corner, well, someone's going to be calling someone asking for help. So what types of well designs are the most efficient and also the most drillable? And another interesting thing is when you're drilling, you have 1 second data. So every second your drilling rig is giving you data. How do you take that data and connect it with something more interesting? Let's say rock properties. Can we estimate rock properties in real time? And then can we then connect those back to, let's say, a reservoir simulation where we now understand what the subsurface is doing at a much higher, say, resolution? Because even if you think about it, gamma ray, what's the area of investigation for a gamma ray tool? 10 meters, 5 meters, there might be some better ones. 1 second drilling data, in 1 second, you've drilled a centimeter maximum. So that's a much higher resolution now that if you can invert for rock properties, you can get some very interesting rock geology information out. And heat flow, how does the heat flow on the pore scale all the way up to the reservoir scale? And then how do you recover and use it? And then finally, how do you enable these systems? And one thing that we're trying to do at the university is for all of our large projects is earmark some funding for these more community type approaches in order to try and enable this community engagement. Because if you ever talk to a company, they all say working with the community is awesome. If you ever go ask a company for funding to work with the community, 90% of the time they'll tell you to go talk to the government. And then the government will turn around and say, go talk to the company. So by allowing us to say, earmark some of this funding will give us an interesting opportunity to really pull in, let's say, people in policy or education and really start moving, let's say, educate or engineering past, this is the engineering solution, now it's the engineering and community solution. So there's some hopefully exciting things coming out of here fairly soon. But that aside, so that's all coming up. So over the next couple of summits, I'll be excited to start talking through some of these things that we're working on. What I'm going to do today is going to do a bit of a primer on how drilling and drilling modeling could, let's say, help enable both drilling optimization, but also potentially start tying in with a geology or reservoir type modeling workflow. So if you think about it, what do we work with? You have a reservoir somewhere deep underground. All of you here are reservoir modelers, reservoir engineers. You know what the rock is down there. You you model your reservoir, and then you say, we want a well here. You call the driller and you say, thou shalt drill well here, and you call me when it's done. There's typically not too much interaction between those two. The driller gets this, and what tools does the driller have? The driller has a drilling rig, which shows up at some location at the surface. This location may be directly above your reservoir, or it may be off a little bit to the side. So let's say maybe you're drilling from land into a sub-ocean reservoir. Maybe you're drilling in a city and you want to get to a reservoir in the middle of the city, but your rig has to be somewhere at the edge of it. Maybe you're drilling horizontal wells, whatever it is. So your tools are all at surface, and you're using a long skinny pipe. Think of a piece of spaghetti in order to transmit all this power from the surface down to this really fancy thing at the very bottom of your drill string, which is called the drill bit. And you're expecting this drill bit to spend its time and its life chewing through rock and making your hole deeper. Now, an interesting thing with this is drill pipe. If you think of 10 meters of drill pipe, so let's say this steel column right here, you expect it to be very stiff. You don't want this building to move. Now, what happens when this building is 7 kilometers tall? That little piece of metal becomes very noodly. So there's a lot of dynamics, a lot of, let's say, movement that can go into it. And that becomes an extremely interesting dynamics problem that needs to be understood if you want to know what's happening down the drill bit. So data, if we're trying to understand the system, what data do we have? Not very much. We know what's happening on the surface. We know a little bit of what's happening downhole because we have a sensor down there that's transmitting data up. If you think that NASA has it hard with a 100 kilobit or maybe a megabit connection from Mars, the typical data rates from sensors downhole is about 15 to 20 bits per second. Some of the newer technologies are maybe a kilobit per second. So you have very little data coming up from downhole. So you have a little bit of data coming up, nothing along your drill pipe, and you have all your surface data. But you have a very complex dynamic system. So what if we take our knowledge of the physics of the system and create something called a soft sensor? So a soft sensor is an estimator that can in real time update itself and estimate the state of what's happening at a specific point. So let's just say we want to understand what's happening at that star. How will we do that? So first, let's start with a dynamic problem that's very well understood, which is something called stick slip. You rotate at one end, the bottom end doesn't have enough power, it stops every once in a while, sticks, your drill string spins up or twists upward and stores energy. Once you have enough energy, the drill bit releases, drills for a little bit, runs out of energy, stops. So it's this very cyclic cycle, and it's very frequently seen. There are systems out there now that control for it. And in the simplest fashion, you just have a mass on a spring, and you have a damper, and that's your numerical model. If you have to have a more complex wellbore, though, that model doesn't really work. So here's 2 examples of field data with stick slip. The example on the left is a more symmetric, typical type of, let's say, stick slip, where you, let's say, start rotating the surface. Surface RPM is around, say, 80, 90 in this case. It's that little narrow red line. And then that oscillating sine wave is your downhole RPM. So this well had a high frequency data sensor in it that was recording on memory. You couldn't see this in real time. You saw this 2 weeks later when the sensor finally came out of hole and was downloaded. So a very, very cyclic pattern downhole. And then at the surface, your torque, so the energy that's going to the system, has that nice symmetric saw wave. Example on the right is also stick slip, but has a slightly different character. It's a slower buildup, faster release, slower buildup, faster release. So what's happening for these two scenarios? Very similar wells, very similar overall operations, different physical, let's say manifestation. So what it was is a deviated wellbore. You can have a friction, a nonlinear friction or a sticking force occur either the drill bit or along the drill string itself, so along the drill pipe. And what we saw in these wells is the stick slip started before you started drilling. You're off bottom, you're not making hole, you start rotating and you're sticking to the side of the hole. You get on bottom, it gets even worse. So how do we model that? A mass on a spring doesn't do that. So you pretty much start off with a wave equation. You transmit energy across a unit of drill pipe, and you have, let's say, damping or a source term. So that's S, that's that S omega X, where you enable some form of friction. And the frictional, the shape of the friction is effectively a jump discontinuity. But that aside, what does this look like? So here we have, I'm going to have a animation. The two plots on the left are going to be torque and RPM from surface to the bit. So that wave that you'll see traveling upward and downward is the actual drill string spinning up and stopping in different depths. The picture on the right is going to be the surface data and then the downhole or the bit RPMs that you will actually see from a sensor. So if these work, so you can see that you twist up the drill string, the torque is increasing, bottom RPM is still 0. You exceed a certain stick force and then the bottom releases. And you have a huge amount of energy that is released by that drill bit. Now imagine your little poor drill bit with some electronics above it being flailed around or like rattled around the drill pipe. How long do you think this tool will last? Not that long, or it will last less long than the manufacturer intended. And you know how drilling works. If you break something, the rig will blame the service provider will blame the rig, and both of them will blame the operator. So it's generally a bad idea. So how do you, let's say, model this and then create a control system that can go around it? So those exist, but the interesting thing here is we now can understand the dynamics of the drill string itself. What we can do then is the dynamics are understood. Now let's look at the bit-rock interaction. So once we can get the energy down to the drill bits, we can look at, let's say, the energy that's going to be going into the failure of the rock. One way you can look at it is more of a mechanical model. How much are you digging into the rock, and then how much, and then how fast are you spinning? The other way you can look at it is how much energy are you putting into the rock itself, and how much of that energy has been converted into rock failure. And what you can do with this now is in real time, you can fit these parameters and start, let's say, guessing of what's happening downhole. So the model that's on the right, so that's a energy-based approach similar to mechanical specific energy. The key thing here is your fitting factor, so fudge factor as we all try not to call them. Our fitting factor is a efficiency multiplied by rock strength. So if you assume a constant bit efficiency, you can estimate rock strength. Or if you assume a constant rock strength, you can estimate bit efficiency over time. So what's the speed of change for each of these? Rock can change fairly quickly, but it's typically a large step change as you go from formation to formation. A drill bit goes from efficient to inefficient as it slowly wears. So you have two different ways of how, let's say, these two parameters change over time. So you can use that to your advantage to try and estimate what's happening. So as a first example, let's assume you know everything about the system. You have a full simulation, you know what the bit rock is doing, and you turn your estimator on and try to estimate your bit rock interaction. So this plot here, the red curve is the estimator running, and then the blue curve is the real, let's say, or the simulated reality. When you're off bottom, everything's matched well. You tag bottom, your drill bit has now engaged. The estimator doesn't know about the rock yet, so it needs to be able to guess in real time, or pretty much guess and update itself until it gets to a place where you're close to what the rock is doing. Over the course of about 30 seconds of simulation, it's able to guess the parameter and then come to a bit rock interaction parameter that's equivalent to that original simulated parameter. And this shows that in simulation, this estimator can actually work. So if we now look at field data, what does this now start to look like? So here's just an example where we have some data. We have a fairly constant weight on bits. That's that blue curve. Your ROP, so that's that red curve, is oscillating a little bit, but still is fairly consistent. Your differential pressure is a nice flat straight line, so you have a constant torque. Your standpipe pressure is also constant, and then bottom hole, your surface RPM is around 80, and then that green estimate is what the model is estimating to be a bit RPM, and then that darker blue that's in the background is a pretty straight, let's say, measured RPM. That's a lower frequency measurement. So what we have here is fairly consistent drilling. Rock isn't changing. Now, what do these, let's say, bit rock interaction parameters look like? So same plot, now just looking at torque. Torque is this extremely noisy, let's say, concoction, because again, you have a lot of force and energy that's going to the system, but your estimation is now following an interesting trend. What does this trend actually mean? It's a combination of bit efficiency and rock strength. How do we separate between those two? Work in progress. But it still means that that combination now is trending, and you can potentially start using this to tell yourself, how is the bottom hole changing, and how do you, let's say, pull out a rock strength type estimate from down hole using just drilling data? The drillers in the room will tell me, oh, I just look at the torque spike, and that's a change in parameter. Yes, but how does the machine know that? So this is to enable the machine to be able to do this. So one other way of looking at this is looking at, say, a physics versus data-driven type approach. So we know that drilling energy is a combination of efficiency, or drilling efficiency, and your rock strength. The efficiency can either be your drill bit or some other dysfunction that's happening in the system. So using physics, we can try and estimate, let's say, this drilling energy, and if efficiency is constant, then we can get rock strength, etc. On data, one interesting approach we could potentially use is, imagine we have, let's say, an environment where we've trained the model on good drilling, or on, say, drilling within a specific formation. When we are trying to predict forward now, a machine learning or a data-driven model will always mispredict on data it has never seen, because typically your data-driven approach is fit on a training data set. If your parameter space that you're trying to, let's say, predict on, it will behave erratically because it's never seen that data before. If the model's overfit, it'll be even worse. If it's, let's say, fit well with some physics built in, it may give you a good estimate. But let's take an example. Here's some drilling data over the course of about 24 hours. If you look at it, the top half of this drilling data set is good drilling. So it's nice, consistent, nothing really interesting is happening. And the reason why we can say that is if you look on that far right track, that is mechanical specific energy. So that's the amount of energy being put into drilling. It's trending consistently. It's noisy, but it's trending consistently. Then right as that orange starts, so that's the bad drilling, you see that there's a step change in that MSE. So there's the amount of energy necessary to drill has suddenly jumped. Either we're in a different rock or the drilling itself has gone into a poor type drilling. So if you take this data set and you say, this is the good drilling, and now we want to test it on the bad drilling, just for fun. What happens? So here is the, let's say, the example. So the blue curve is real. Sorry, the red curve is the real ROP, and then the blue curve that's on the far left track in the ROP is the actual data. If you look at that prediction, the prediction, so that red scribble is more or less on top of the blue scribble for the first half of that data set. In the bottom half, you can see that the prediction now is significantly mispredicting what the actual ROP was. What does that mean? The model's wrong. But if the model is wrong, what else can we say from that? There was a change in the operating parameters, and that in itself can give us now a flag of The model is not mispredicting, something has changed downhole. So now this can be used for, let's say, activity event detection. Simply, and this is how we can get around, let's say, small data sets on the, let's say, the machine learning side. But where are we going with this? Rock strength logs. Wouldn't that be awesome? Can we create a log of rock strength for an entire well? And then can we tie that in to a reservoir simulator? In reservoir simulation, you have a good idea what stresses are. You know what, let's say, the formations are to a certain degree. Can that be tied into drilling operations? And then can real-time drilling data help feed the actual geology model in a reservoir simulator? And then from this, can you have a drillability prediction? So imagine that you're designing an interesting well. Can you have, let's say now, a metric of how feasible is this specific well design versus another well design based, let's say, economics, on stresses, on, let's say, potential drilling problems, etc. And then finally, what we're doing at the moment is with supporting Ever in drilling the deepest directional geothermal well in history. That's currently being drilled, and my team at the UFC is getting daily drilling updates and learning what getting an email at 3 o'clock in the morning is. Feels like. They ignore it right now, but I actually have to be on top of those. So I think with that, thank you to our sponsors. So Provincially, NSER, Calgary Innovates, MyTax, and then quite a few government and industry partners as well. Questions, please reach out or take a look at the yet to be updated GEOS website, because our press release is coming out at some point in the next foreseeable future.
Such as a promise. Thank you, Roman.